But at the very end of the last topic, we were talking about like the degree of trees. And the degree of any given node is the number of children it has, right? So if you look at A has 2 children. But if we scroll down, we'll see an example of a tree like H, for example, has no children. D has 1 child, it's H. Then the question is asked, well, what's the degree of the whole tree? You simply take, well, whatever the biggest degree of any of the nodes is, and that's what we would say the tree is. We're going to talk about binary trees. And a binary tree is a tree with a degree 2. No node can have more than 2 children. It can have 1, it can have 0, it can have 2, but it can't have any more than 2. That's the rule. So a binary tree. Here's a binary tree with 9 nodes. Each node has no more than 2 children. And an interesting thing about a binary tree, where it doesn't necessarily need to matter, but often it does, the direction of a node matters. Often we'll refer to the children of a binary tree as the left node and the right node. So here B is the left node of A, left child, and C is the right child. And that's kind of like, we can kind of think of this as, like, it matters what's the left and what's the right. What it is doesn't necessarily need to matter, but there's a positionalness to it. In the same way that I can have an indexed list, where the elements in the indexed list don't have any important ordering. I just added a bunch of things at random. But the fact that there's an index 0, an index 1, and an index 2 is still a thing. It's just maybe it didn't matter. But that positionalness does matter. So a binary tree is one where each node has no more than 2 children. It's a Turi tree, a tree with a degree arity of 2. It's a binary tree. If a node has children, they're referred to as the left and right child. And the left and right child will, if you remember back to the definition of a tree, the left and right child will then themselves be roots of subtrees. So sometimes they're even called the left and right subtree if you're referring to like everything over there. But the child, the left child, is the root of the left subtree. Position matters. It matters if the subtree is the left or right. And a recursive definition of a binary tree is an empty tree or a tree that has a root whose left and right subtrees are binary trees. And this is recursively applied. So here's a quick little thought experiment thing. What would a unary tree be? Not a binary tree, a unary tree. What would you say?
A linked structure?
Just a regular old linear linked structure. Because I guess trees are linked structures. They could be depending on how they're implemented. But a regular old linked structure, a linear one, yeah. Each node has no more than 1 child node, 1 successor. So you'll notice that a tree is a generalization of these linear collections we have. All linear structures are kind of like, they're trees, but they're restricted. And then a tree is just more general, which is kind of neat. So traversals. With the simple linear data structure, I know I've hit this point hard, but it's going to be hit again just to get to the next point. A simple linked data structure, the order in which the nodes are traversed is rather natural. If I say you're starting at the head, which is that light blue node, and I ask you what comes next, what's your answer?
The light green node.
The light green node. And then what comes after that? The slightly, who's purple? It maybe. I don't know, cyan, I don't know, teal, whatever color that is. And then after that, there's a black one. Now, there's no rule saying the traversal couldn't be some weird order of things. Now, don't get me wrong. I don't want to get you confused with the traversal when I say next thing. Maybe I should say subsequent thing. I'm talking about a traversal of the elements, not necessarily which node's next is. Because I could, if I want to traverse these elements in reverse order, like I could create an iterator that goes backwards. I could traverse them going like light blue, turquoise, whatever color that is, the green one, the black. I could go any order I want, but I'd have to tell you, the natural ordering is you start at the beginning and you go to the end. Okay? Other traversal orders, yeah, could be defined, but they're less typical. But when I ask you here, this is a nonlinear data structure. And I say, here's a tree. You're at E. I'm not starting at the root. I don't have to start at the root. Let's say you're at node E. And I say, what comes next? It's kind of, maybe you've got an answer. What comes after E?
Null.
Null. Interesting. Any other ideas? I want to be clear. Null's right, but also wrong.
Nothing.
Depends. Nothing. Null. Good enough. What? F doesn't come after?
Does it reference back to B?
Maybe. I don't know. So maybe B comes after? Cool. Maybe. The point I'm making is we could come up with whatever traversals we want, just like with the linear collection. But unlike the linear collection, where there was one really obvious traversal, let's say I say A. You're at A. What comes after A?
Depends.
Depends.
Do I want to go left or right?
You want to go left or right? The point is there's no obvious answer. And maybe you've got one that's a little bit more obvious to you, but you've got to concede that it's not as obvious as starting at the beginning of an array. This is a little like, well, it depends. Now, that said, there are a few common, popular, whatever you want to call it, traversals that we'll cover. One set are like a depth first style. Another one is a breadth first style. But the searches that we're going to do 4. There's going to be a pre-order, an in-order, a post-order, and a level order traversal. They're all different traversals. They're all traversals. We're going to define them. They're quite intuitive, in my opinion. But the order that they are, but which one is the best one? Of those 4, which is the best? Which is the right one? What's the natural one? Well, it's not really a reasonable question to ask, because there is no natural one. It's a nonlinear collection. So pre-order. I'm going to tell you something. The pre, in, and post are going to be remarkably similar. Their algorithms are hilariously similar, with a trick to never forget the algorithm, but we'll get there. So a pre-order traversal is one where you start at the root. And remember, each tree has a root and each subtree has a root. So this is a recursive definition. You start at the root. You access that node that you're at, so like that root node, whatever it is, whatever that means in your context. Here, in the trees we were looking at, they were just labeled like A, B, C, D, E, F, G, H, and so on. So when we say access, we'll just get the data from it, where the data is just that label, let's say. So once you access the data at the root, you repeat this process on the left subtree. And once that is done, you repeat this process on the right subtree. So notice that the root of the tree subtree is accessed before or pre any recursive calls. So let's follow this algorithm. We'll take our time. I won't go too fast, at least. We start at the root, A. We access the element. We access the data. Whatever that means here, we'll just say the label. So we are at A, and we access it. So we get A. A starts. Then we go to the left subtree. There, we're at the node B. B is the root of that subtree. We access that node, B. So we got A, B. Then we go to the left subtree. We're at the left subtree, D. D is the root of that subtree. Access the root. Great, D. We go to the left subtree. Is there a left subtree? No. We're done. Okay, great. So we're done the left subtree after D. Then we do the right subtree. Well, H is the root of the right subtree. Access it. So here's what we've done. We've got A, go to the left. B, go to the left. D, go to the left, nothing there. Go to the right. H. Go to H's left subtree, doesn't exist. Go to H's right subtree, doesn't exist. H is done. We go back to D. That means that one's done. Go back to B. We just finished B's left subtree, so now we go down the right subtree. E. Go to the left, doesn't exist. Go to the right, doesn't exist. Return, just finished B. Return, there. We just finished A's left subtree. Go to the right subtree now. Okay, C, left F, left I, left doesn't exist, return, right doesn't exist, return, right G, left doesn't exist, right doesn't exist, return, return. That's the order. In this particular case, it's A, B, D, H, E, C, F, I, G. That's it. Pre. Get the value from the node before any recursive call. Then repeat the process on the left subtree until it's done. Then do it on the right subtree until it's done. I realize I just said left and right, but I use my left and right, so there. So, who wants to take a wild guess? If pre-order did access that node before the recursive calls, who wants to take a wild guess without even looking at it? Where do you think we access, relative to the recursive calls, where do you think we access the root element in the in-order traversal?
In the middle of the recursive?
In between, yeah. So here, it was, if the node exists, access the node, pre-order on the left, pre-order on the right. The access the node was before, pre. Now look, it's in between, yeah.
Is that, it says pre-order traversal in the in-order traversal, that's supposed to be?
Oh, that's totally supposed to be in order. So someone can make a pull request and fix that. So here's the algorithm. Yeah, those should be recursive calls to in-order traversal. So notice that the root of the subtree is accessed in between the recursive calls. So what do? Let's follow the algorithm. We're at A. Great. We don't do anything with A yet. We got to do the left subtree first. Okay? Now we're at B. We don't do anything with B yet. We got to finish B's left subtree first. We go to D. Don't do anything yet. Got to finish D's left subtree first. Doesn't exist. Return. We're done D's left subtree. Access D. D. Go to the right. Go to the left. Doesn't exist. H. Go to the right. Doesn't exist. Did I just say go to the right? Go to the left. H. Go to the right. Return. Return. We just finished B's left subtree. B. Go to the right. Go to the left. Doesn't exist. E. Go to the right. Return. Now we're all done B. Return to A. Now we can access A because we finished A's left subtree. And just going more. Okay. C, F, I. Access the data. Return. F. C. G. Done. There we go. And then finally, we have post-order traversal. Who wants to take a wild guess where the access to the current route is relative to the recursive calls on the post order? Let's get someone different this time. Someone else different this time. What do you say? After. If the name doesn't make it obvious to you, I don't know what's going on, because it
To be
should.
fair, it was only this year that I realized post meant after.
Oh man. Well, post means after if you didn't know that. Pre means before. And in means like, in. That one shouldn't shock you. Post order. And once again, this should say post order traversal. So we do the left, we do the right, then we access the node. So let's follow the code. Go to the left, go to the left, go to the left, go to the right, go to the left, go to the right, H, D, E, B, I, F, G, C, A. That's it. You should never forget these algorithms. They are remarkably simple. Base case, does the node exist? Pre-access, recursive left, recursive right. In, recursive left, access, recursive right, post, recursive, access. You should never forget. And because you're never going to forget these algorithms, if I asked you to do this on like a test or something, everyone should get perfect on this. Because you just follow the algorithms. What does the algorithm say? There's no magic. Take your time. You'll be in great shape. Yeah?
Is that an end for the panel?
No, not at all. But it could be. Could be. Could also not be. I don't know. Now, level order traversal. Oh, this is a tricky one. At least the algorithm is a little bit more complex. But the idea is rather simple. You start at the root. I'm going to tell you the level order, and you're going to tell me if you can figure out what I did. The level order in this particular example is A, B, C, D, E, F, G, H, I. What did I do? Obviously, I started at the root. Then what?
Then you went to the left. And then as soon as it exists, you call it, you get the data. And you go back if it exists.
Well, hold on. You're thinking, I like what you're thinking. I like what you're thinking. You're trying to find that recursive rule and how it all worked.
I don't think there's a single recursive rule you can do.
There is one, but don't do it.
It's complicated.
This one, don't even think recursion. Just explain to me what I did. Why is it A, B, C, D, E, F, G, H, I?
You just did all of the letters from top to bottom, and then you went top to bottom, left to right.
Exactly. Right? One level at the time, starting at the roots level. That's all I did. Now, you could implement this recursively. Don't. It's not nice, it's not clean, it's not natural. And in fact, there's a reason the other ones worked a little nicer with a stack. In fact, actually, I want to take a moment here and emphasize something. Those first three traversals are... Do they in any way remind you of anything you've done in this course so far?
Stacks.
Okay, yes. Yeah. Can you get a little more specific on anything in particular you've done? Does it remind you of anything?
Kind of like the maze solver.
It absolutely is exactly like the maze solver. It's just the order of the things is a little different, but you figure with your maze solver, you use a stack, right? And everything you do with recursion uses a stack implicitly because of the system, the call stack, right? Each time you put a frame on the call stack, it's like you're using a stack. You figure on assignment 2, when you solve the maze, you had some set of rules. Now a maze isn't a tree. It could be. More generally, it's a graph, which is a further generalization of a tree that we're not going to really hit in this course. But you figured, with the maze solver, you checked up, you checked right, you checked down, you checked left, right? Or maybe you did, yeah, up, right, down, left, probably, right? 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Obviously, we would always check the current node first to be like, okay, is it the end? So really the maze solver is like a pre-order traversal. But you didn't do it recursively. You did it with a stack. Each time you found a neighbor, you'd put it, if you looked up and that neighbor existed, you'd push it onto the stack and then restart the loop, take the top of the stack. Pre-order traversal, you could take and modify the pre-order traversal code I gave you slightly, and you'll have a working maze solver for assignment 2. I could have given you assignment 2.5, and you'd have like a DFS recursive maze solver, and it would work just fine, and it would be hilariously simple. So the pre-order traversal, it's a maze solver. It's doing a depth first search. It goes all the way down until you kind of can't go anymore, then it backtracks. But notice how with the recursive ones, when I went down, let's say it was pre-order, I did A, B, D, I went past D, didn't exist, and I went back. And then I did H, returned to D, returned to B. See how it like backtracks and then carries on branching paths? Goes down, up, right? It's exactly what your maze solver was doing. But you just thought about it a little bit differently, but it's the same thing. I could implement this pre, post, in-order traversal iteratively, not recursively, iteratively, really easy with the use of a stack. Very easily. The way I would do that would be basically what you did in assignment 2 with the maze solver. It would be very easy. This level order traversal is an entirely different style of searching. Or traversing, let's say. Because really searching would be if there's traversing with a goal to find something. You could do a maze solver with a queue. And if you were to do that, you would have a breadth first search, where you don't go all the way down and then backtrack. You just kind of like spread out until you find a solution. In fact, you did that in assignment 3, but you used a special maze, or a special queue, a priority queue, that guided that breadth first search intelligently towards the end. So you actually did a modified, enhanced version of the breadth first search. If you were to implement level order traversal, it's a breadth first search. You start here, and then you go to everything step 1 away, step 2 away, step 3 away, and so on. You're just continually moving further away. The way I would implement this, I wouldn't do it recursively. I could, don't. But the way I would do it is with this pseudocode. Obviously, it's a little bit more verbose than the other recursive ones, because recursion tends to be nice and clean and elegant like that. But here's what we do. If the root node exists, so this is not recursion. You have to take your recursion hat off. Think back to loops. If the root node exists, enqueue the root node to a queue. So at this stage, we have a queue with one element in it, right? Let me draw it for the sake of understanding. I'll draw my queue like this. So if I go to my tree, it's A. A, the root exists, it's A, I enqueue it. This is the rear. We go into this end, we come out this end, okay? I enqueue A, all right, it goes in there, A. Great. I'm all set. Now what? Well, the queue is not empty. Queue is not empty. DQ the node. I take out A. I still have A though. I've got A. I access that node. Okay, great. That's just like printing out A, whatever. If the left child of A exists, you enqueue it. If the right child of A exists, you enqueue it. But we do it in that order, left and then right. So the left child, let's do this, is B. So we enqueue B. And then C. We're done with A. So we DQ, because we say, well, the queue is not empty, it's not empty, DQ B. Enqueue, print it out, enqueue its left and right children if they exist. Okay, DQC, or DQ, because it doesn't, it's not empty. Enqueue its left and right children if they exist, that's F and G. Do note that the only reason the queue is moving down is because I'm too lazy to rewrite it all, right? Make sure that's clear. It's not meaningful in any way. Okay, Q is not empty, DQD. Enqueue its left child doesn't exist, so we don't. Enqueue its right child, H. DQ, we get E. Enqueue its left child, well, it doesn't exist. Enqueue its right child, doesn't exist. Okay, great. Oops, I said DQE and I never did. Now we DQF. Enqueue its left child. Enqueue its right child, doesn't exist. Q is not empty, take it out. Enqueue its left and right children, well, they don't exist. DQH. Enqueue its left and right children, doesn't exist. DQI. Enqueue its left and right children, doesn't exist. Q is now empty, the loop stopped, we're done. That's the level order traversal. The rule was, look at the node, enqueue its left and right children. Imagine I was doing this with a stack. Imagine this was a stack. Okay, we've got A, put A on the stack, then put its left and right children. Now the order would matter, but let's say I put like B, C. Okay? Peek at the stack, get its other children, and you can see, like as I'm pushing what node we're currently at, and then as I'm popping, we would return to one of the parent nodes, right? Yeah. Cool. So it's actually, we could actually take this algorithm and replace the queue with the stack, and it would be interesting to see what the order would be. Now, which one you push first will have an impact on the order, because maybe it ends up doing the right child first instead of the left child. But perhaps that's not as important as getting a sense of how the stack and the queue, that choice of data structure and just the properties of those data structures has an impact on it changes the style of the search completely. Pre, in, and post, they're all variations of depth first searches. You go down and then up. And yeah, it kind of mattered when you accessed the current node, fine. But they were depth first searches and stacks, that's great. Down and then backtracking. A queue, that was the spread out. It goes breadth-wise. Yeah. So, with the iterative level order traversal, a queue was used. I basically covered all this a moment ago. Yeah, let's go full screen. Am I recording? I better be. Oh, good. What would happen if a stack was used? Well, we just kind of covered it. Great. So now, time to think a little bit about the computational complexity. And there's a couple things I want to remind you of, but I don't want my reminders to lead you astray. Because the question I'm asking is going to be very precise. We got to make sure we're being cognizant of that precision and what words I'm using. Now remember, when we were doing a computational complexity analysis of recursive things, the question was, how many times is this chunk of code going to need to be run? And when we looked at that linear search the recursive linear search, each call made another subsequent recursive call. And we knew that each time it's going to make one call for each of the n elements in that list. So we knew it was linear. But then, when we looked at Fibonacci, remember Fibonacci was terrible because Fibonacci had 2 recursive calls for every element. And that gave us that 2 to the power of n. But we have to be aware of what is n? What does it mean? So I don't want knee-jerk reactions. I want you to think. In fact, maybe talk amongst yourselves. I'll give you a minute. Consider a binary tree with n nodes. If all n nodes, here, actually, I think I explained it too much to give you the exercise of thinking about it. But here, if all n nodes need to be visited, what is the computational complexity of visiting each of the n nodes? Don't even think about the code. If I have to put my finger on all n nodes, how many things do I have to put my finger on? N. So if I had a tree with n nodes, it would be like n units of work. If I doubled the number of nodes, how much more work do I need to do? I have to put my finger on twice as many things, exactly. But now you're thinking like, well, hold on though, because I remember when you go and you look at those recursive ones, each one of these had 2 recursive calls, right? And you're remembering that when we analyzed Fibonacci, Fibonacci had 2 recursive calls, and because of that, we had 2 to the power of n. But now it sounds as if I'm saying this is linear. Yet it had 2 recursive calls. But this is because we have to be very careful about what is n. When we talk about computational complexity, it's always relative to some input size. But that input size and what it means could be 2 very different things in different contexts. If the question was changed to be, consider a binary tree with height h, what is the computational complexity of this algorithm? Well, now it becomes hopefully a little clearer about what is n. With Fibonacci, n ultimately corresponded to the height of that tree. Because we needed to know, if I needed that nth Fibonacci number, I need to go all the way down to get to like 0 and 1. But each time I went down, I had to branch out twice at each time, and that's where 2 to the n came from. Here, the question was, I have n nodes. So I have a tree with n things in it. N wasn't the height. N was the number of nodes, and the traversal just requires me to put my finger on n things. But because of the relationship in a binary tree, when you've got this doubling each time down, that relationship between the height of the tree and the number of nodes in the tree is going to be on the order of 2 to the h, where h is the height, let's say. Then it becomes that exponential thing. So if the question was, given a binary tree of height h, what is the computational complexity? Well, relative to h, it's exponential. It's 2 to the h. But if I say, given a binary tree with n nodes, well, it's linear, relative to the input size being the number of nodes. Where if the question was about h, it's an entirely different question. If this is making you think, oh no, now I need to keep track of it, I think you're thinking too hard and looking for patterns beyond the superficial. What is h? What is n? What do they mean? And the relationship between a binary tree should be pretty straightforward. If not, let's draw it and make it as intuitive as possible. I don't know if this is even going to work. Each time I go down, I double. So I have one thing in this row. Then I have two things in this row. And then this will double. So now I have four things. And then this doubles. Or sorry, this doubles. You know what, let me draw these to make sure it's really obvious. Right? So now how many things? 1, 2, 3, 4, 5, 6, 7, 8. And then down here we'll have 16. It's growing really quickly. This is the height, right? 0, 1, 2, 3, 4, height of 4. And this is the sum, the total number of nodes. It's not just the last thing, it's the sum of all. So it's 16 plus 8 plus 4 plus 2 plus 1, right? In fact, how many nodes are there always? If I have 16 down here, how many nodes are above it?
15.
It's always like 16 minus 1, right? Because 16 and then 8 plus 4, so 4 plus 2 plus 1 is 7, plus 8, 15, that's 16. If we were to do this again, we'd get 32. But it would be 32 minus 1, would be the number of nodes above it. Anyways, the point I'm making here is if I asked you relative to h, it's a very different question than asking you relative to n. Any questions about any of that? So, an interface. Let's say we want to make a binary tree. We actually want to code this. We're going to do it with a link structure. So the implementation would be a link structure. So we're going to need some like nodes and whatnot, but it won't be a link, like it won't be the nodes that before, where each node had data and a successor. It'd have to have like a data and then a left and a right child. But that's implementation details. We're worried about the interface. What do we want a binary tree to do? Check if an element exists in the tree, right? Hey, binary tree, does this exist in there? Count the number of occurrences of a given element, assuming duplicates are allowed. Check if it's empty, get the size. Traverse the tree. Fortunately, we just learned about a couple traversals, so we've got a couple options there. But add an element. Remove an element. Those questions are a little bit more complex because, well, adding and removing to a stack in a queue was very straightforward. Where do you add to a stack? The top. Why? Because that's the stack. Where do you remove? The top. Because that's the stack's definition. A queue, similarly simple, but they were opposite ends. There was no question. Where do you add? The rear. Why? Because that's the rule. Where do you add to a bag, though? Well, that kind of depended, right? Was it a sorted bag? Was it just a regular old index bag? It's going to be kind of the same with the binary tree. You want to add an element? Where? How? Why there? It's going to depend. Maybe we've just got a general tree where I just want to be able to add things arbitrarily. Or maybe my tree has some sort of ordering where it really is important how things are added or removed. So we can't go and implement a regular old binary tree. We can define the interface, but how we add and remove is really going to depend on specific implementation requirements, specific requirements of the type of binary tree. So a binary tree, with add and remove, what's wanted means depend on the type of binary tree, similar with a bag, yeah. So here's an interface. Here's an example interface for our binary tree. You notice it extends the iterable because we want this to be able to return an iterator. Add. Well, we know we're going to want to add something. How exactly it gets added, I don't know, but we know we're going to want to add something. I want to say add this element, where T is the type of element I want to add. Same with remove. I want to remove a specified element, and they'll return Boolean to let me know if it worked. Contains, that just searches to let me know if the thing exists or not. Count the number of occurrences of a certain thing. Size, and then we've got a variety of iterators. We have to have a regular old iterator because that's the interface dictates it, but we can define additional iterators, pre, in, post, level. For the sake of having them, we can implement them. The regular old iterator is going to be one of those four. I don't remember which one it is. I'm assuming pre, but I could be wrong. So there's the interface. Now, there's going to be no binary tree implemented directly. Like the bag, we're going to define subtypes with the interfaces. But we can think about certain things we would want in the implementation regardless. One way to implement a binary tree is with a collection of linked nodes. Use a size field to keep track of the number of elements within a tree. And use a field to reference the root node. So you can think of like a linked queue. We had a field for size, and we had a field for, well, the front of that linked structure that represented the front of the queue, the head. A binary tree node, it's going to be another node class. But this binary tree node is a little different than the other node class because it doesn't just have one, it doesn't have a next field, it has a left and right field. So if I ask that binary node left, it gives me the root of the left subtree, the left child. Similarly with right. And it contains some arbitrary data, whatever. Yeah. So we can make a node a standalone class. I could go right-click on my source folder in IntelliJ, new class, create a new node. But if I do that, I'm going to have a problem. Because chances are, unless you made it an internal class, the node class for your queue was a standalone class. It didn't have to be. You could have made an internal class. Maybe you should have. But if you had it as a standalone class just in your source folder, if you go in there and you see node.java, it already exists. And it exists as, well, the singly linked structure node. Data, next. We wanted to find a node that's a little different. Data, left and right. There's two workarounds. One, well, just don't call it node. Call it binary node or something. There, problem solved. Or, perhaps better, would be making an internal class for the linked implementation, for your binary tree implementation. Make it an internal class. That's why this code, which is taken directly from a linked binary tree implementation, that's why you see private static class node. Because it is an internal class within some code I've already created. And this is what it would look like. Private static class node, T, data, left and right, some general constructor that takes the data that sets left and right to null, and then just some getters and setters, accessors and mutators. So of course, this class is mutable. I mean that like I have mutator methods. I can create it, I can set things, but I can like modify them and change them after they're created, which is not intrinsically bad, but as a theme that we've been hearing since the beginning of 161, this can be a recipe for disaster. It makes testing a lot harder, it makes reasoning about your code a lot harder, but it is what it is. So it's a lot of things with data structures, mutability, well, we deal with it. Because that's kind of the nature of data structures. We want to be able to add things and remove things and modify it. One way to kind of, so if you go to the course website or the GitHub repo, you'll find this as a standalone class with relevant unit tests. Because, you know, we write tests, good. But one way to eliminate having to need to test this is, well, if you write this as a private inner class, you don't really need to test it directly. Kind of like private methods, you don't really test the private methods. You test the interface, you test how you use it. And by doing so, presumably you are indirectly testing the private methods because they need to work if everything's going to work properly. But if it's a private inner class, you can eliminate the need for writing unit tests directly, so that could be kind of a win, just as an FYI. And yeah, let's stop here for today.